My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So hope you are well and safe from corona pandemic. So we know that we are staying in a corona pandemic situation, so we cannot continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that Department of Physics, Pabna University of Science and Technology has started its online program, including the online international physics webinar. We have successfully completed our 119th international physics webinar. Today it's our 120th international physics webinar. So we're trying to adjust with this new normal situation. So the aim of our program is to motivate and encourage our students in this corona pandemic situation. So we have invited a lot of speakers from all over the world, including 2 Nobel laureates. Today is very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and American Association for Variable Star Observers, USA in physics. And we have with us here today Dr. Stella Kafka, Madam, Executive Director and CEO, American Association of Variable Star Observers, USA. She has already connected with us, so I'd like to welcome our speaker. So good evening, Madam, and good morning to your part. Thanks for accepting our invitation.
It's a pleasure to be here. Thank you.
Yeah. We'd like to say thanks on the behalf of the Department of Physics for accepting our invitation. For those who are new, I'd like to inform that we have divided our webinar into 3 parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver her speech with you, and at the end we have a discussion time. In that time, actually, anybody can join with us. So I think you have already come to know the title of this today's International Physics webinar. Title is the Exploring the Universe Through Variable Star, and our speaker is Dr. Stella Kafka, Madam, Executive Director and CEO, American Association of Variable Star Observer, AAVSO, USA. So she has completed her bachelor degree from University of Athens in physics, and MA in astronomy, and PhD in astronomy from Indiana University. You can see her postdoctoral research work from Caltech to American Observer now, and also director of REU PIO programs. We can see her professional activities and publication and awards and honor. So thanks for all of your patience. Now it's time to go to our speaker. So thanks again, Madam, for accepting our invitation. It's your time, Madam. You can start your session.
Yes. So here we are. So again, good evening, good morning, good afternoon, everyone, everywhere in the world. Today, I would like to talk a little bit about how we explore the universe. The universe actually is a natural laboratory for extreme phenomena. It is also providing opportunities for us to test various theories in extreme environments, various physical phenomena in extreme environments under conditions that cannot be replicated on Earth. We will talk about variable stars, why they're important for exploring the universe, what type of information we get from them, and a little bit about their physics. I will approach this subject from an observational standpoint. I'm an observer. I'm a person who observes the universe and collects data. And I will discuss observations and some calculations that help us extract fundamental information about the universe, and also introduce active research areas that the AAVSO observers, the AAVSO community is involved alongside scientists all over the world. This is only an introduction. After this lecture, I would like to encourage you to do some reading of your own and learn more about specific subjects of your interest. The universe is a fascinating place. First, as an introduction, the AAVSO, American Association of Variable Star Observers, was formed in 1911 at the Harvard Observatory with a goal of engaging amateur astronomers in professional astronomers' projects. As such, it is the first association that was founded in order to do citizen science, to connect professional and amateur astronomers and help them collaborate on scientific projects. Since 1911, the AAVSO has grown to be a truly international community. We are serving people who are interested using variable stars for the research projects. We work with educators who introduce astronomy to their students. We collaborate with a very dedicated group of volunteers. And of course, we have our observers, those who acquire data through their telescopes, CCDs, or DSLR cameras, and share this information with the wider community through the AAVSO International Database. As a consequence, we have a very diverse community all over the world. This translates to serving people with different needs, different priorities, different professional preparation, habits, cultural background, individuals who are united under the international umbrella of astronomy. And remember, astronomy is the only science where people without a formal degree are able to make meaningful scientific contributions. And these are individuals, again, who comprise our community and help us do our work. So at the core of our program are variable stars. These, by definition, are stars whose brightness is changing with time within timescales that we can measure. And those changes can be observed from here, from the Earth, and they're not related to the Earth's changing atmospheric conditions. And here's an example. What you see here in this picture is what we call a star cluster, a group of stars that were born together, but they were born with different mass. As a result, they have different evolutionary stages. They evolved in a different way. And actually, this particular picture, this was a composite of 3 different images that were acquired at the same night, and they're subsequent. So pretty much what you see is a little movie. And if you follow this movie, most of the stars do not do anything. So they're very static, they're there, they're not blink or anything. However, if you pay a very, very close attention, you will notice that some of these stars in this image are blinking. They're changing. Their brightness is changing. And it's changing within timescales we can measure. So you can see how frequently they increase and they decrease their brightness. And they're also changing at a level that we can measure. These are variable stars. This is what we mean by variable stars, stars whose brightness is changing within timescales we can measure and within ranges we can measure. Our tools are what we call light curves. We take those variable stars and we actually monitor how they change their brightness with time. And as a result, we create a diagram, brightness change with time. And we plot the changes of this particular star. This is what we mean by light curve. This is our tool to actually explore those kind of stellar properties, record stellar properties in order to explore them. And if you take one of these stars that is not changing in brightness in here, and you plot its brightness variations, pretty much you're not going to see anything. It's a straight line. It's a constant star. It's not doing anything. It's actually staying there. Now, reminding you, variable stars are part of the life cycle of stars. Stars are born from clouds of interstellar gas and dust. They shine by their own light created through nuclear fusion of hydrogen in their core, and eventually they run out of fuel and die, returning some of their mass back to the interstellar space. Their remains can then be taken up into new generations of stars, starting the process again. This process of change that a star undergoes during its lifetime is called stellar evolution. Now, variable star, and actually this is a schematic of different stages of stellar evolution depending on the initial mass of a star and the gas that exists in the star itself. They can actually evolve and they can die at they can follow different stages, they evolve and they die in different ways. Now, variable stars exist at every stage of a star's life, from birth to evolution to growth and death. And they give us very valuable information on the nature of stars. As a result, there is a zoo of variable stars, and these are some of the main categories. In principle, there are 2 main categories. There are the intrinsic variable stars, where the cause of variability lives in the interior of the star, and extrinsic, which are those who seem to be variable before their appearance. So all these subcategories reflect the fact that the reason for variability is multiple and complex. Today, we're going to discuss aspects of those categories, focusing on representative classes. I cannot cover everything. There's so many stars out, different types of variable stars out there. We're going to talk about periodic variables. We're going to talk about rotating variables and eruptive, explosive variables. Please note that these are not exclusive clubs or exclusive classifications. Stars can belong in more than one category. We actually classify them based on the most pronounced characteristic, not the only one characteristic. So let me start by introducing periodic variables. These are stars that do something repetitively, variables that seem to change in brightness in a very consistent way. They do the same thing again and again, and actually, in principle, you can predict their behavior before you observe it and go and take data to confirm it. I will start with binary stars because they are the most common type of stellar variation. But before I do that, I'd like to take a step back and remind you a couple of concepts from your mechanics class and remind you of the concept of Rose-Lobe geometry. The Rose-Lobe outlines the volume surrounding an object with which material is gravitational bound to it. This is a two-dimensional replica of a Rose-Lobe geometry in a binary star system. This is pretty much the Rose-Lobe of each of the two stars, and it's showcasing that the size of the Rose-Lobe depends on the mass of each star in that the more massive star's Rose-Lobe is larger. As it's demonstrated here, the Rose-Lobe is approximately teardrop-shaped. It's a region that is bound by a critical gravitational equipotential with the apex of the teardrop here pointing towards the other star. The apex is at the inner Lagrangian point of the system. Now, based on this geometry, we have three different types of binary star systems. The first one is where the two stars are well within their respective Rose-Lobes. This is called a detached binary. The second one is when one of those stars is filling completely its Rose-Lobe. And in this case, material that lies outside the Rose-Lobe is pushed through the inner Lagrangian point. This is the only place, the only location that it's allowed to actually move towards. And this is what we call a semi-detached binary. There is a case, a really extreme case, where both stars fill the Rose-Lobes and they overflow. In this case, they form what we call a common envelope of material around them, and this is called a contact binary. Today, I'm going to talk about two of the three types of binaries, the detached and the semi-detached. So let's start with the detached binary systems. These are two stars well within their Rose-Lobes that are tied together by gravity, so they cannot escape, and they move around their common center of mass. This is a cartoon showcasing a binary star's orbit. Now, as a reminder, this is what we mean by center of mass. If you have two stars with mass m1 and m2, and the distance, their distance is a, and the respective distances from the center of mass is a1 and a2, then the center of mass equation is a1 times m1 equals a2 times m2. Now, using this equation, we actually get, and this equation actually, a equals a1 plus a2, we can get how far away the center of mass is from the center of from each one of those two stars. It's really important actually because we cannot measure distances of stars, and actually in binary star systems, most of the time we cannot see the two stellar components. All we see is just one dot through the most powerful telescope. And actually more than half of the stars in our galaxy, and actually some say about 3 and 4 stars, belong in binary star systems. So these are extremely important and extremely abundant in the universe. Now, most frequently, we know that a star is part of a binary star system when the plane of the orbit is the same plane as your line of sight. So mind you, in this case, you cannot still distinguish the two stars from each other. even again through the world's most powerful telescope. All we see is a dot. So, however, if you start observing this dot and measure its brightness through whatever means you want, your telescope, your binoculars, or whatever, what you see is that there is, when one star is actually passing in front or behind the other, you see a dip in the brightness of the system. This is what we call an eclipse. This is a purely line of sight effect. The two stars don't necessarily interact with each other other than gravity, and they're not changing their interior. And that is why we call them extrinsic as binary as variable systems. Over a period of time, we'll see the light from the system get dimmer from a short time as one of the stars passes in front of the other. Those stars are really important because by measuring the duration of the eclipses in those light curves, we can find out the size of the stars. And as we, again, when we observe those objects, all we see is a dot. Measuring sizes of stars is extremely difficult in the universe. This is how we do it. If we take Newton's laws of motion, F equals ma, which you know from your mechanics, this allows us to derive Kepler's equation for orbital motion, which is m1 plus m2 times the period, how frequently one star passes in front of the other, equals a3, a to the third power. Where, again, m1 and m2 is the sum of the masses of the two stars in units of the sun's mass. A is the distance between the two stars measured in astronomical units. One astronomical unit is the average distance between the Earth and the sun. And P is the time for one full orbit measured in years, which we measure actually from a light curve. So that is why it's really important to get light curves. The orbital period is very easy to measure. Now, if you can find the orbital separation A, you can solve for the sum of the masses. If you can also see the distances, find the distances between the star and the center of mass, you can use the center of mass equation to relate to the two masses. Now, combining the two equations, Kepler's equation, the center of mass equation, we can solve for the star's masses. And it's extremely important to actually do that, simply because, again, there's no other way we can measure the mass of the sun. Here's another very interesting application. I hope that you've heard about exoplanets, and I hope that you've heard about the exoplanet transit method. This is a schematic showcasing how the transit method works. In principle, it's an eclipse. When you have a planet that is passing in front of a star, in its brightness, the brightness of the star is dropping by a specific amount that depends on how big the planet is. So the planet, in principle, covers parts of the star, so it shows an eclipse. That is what we mean by a transit. What is showcased here is that for larger planets, the depth of the eclipse is larger than for smaller planets. So the most important aspects that we can actually measure the planet's size through this particular method. This method is extremely difficult to make if the planet does not happen to transit. That's why at some point, transiting exoplanets are extremely important in astrophysics. The amount of light a planet blocks in transit depends, again, on how big the planet is. So measuring the transit depth is not enough to measure the size of the planet. You also need to know the size of the star that it's transiting. Specifically, the transit depth is equal to the ratio between the planet's radius and the star's radius. Now, we know of the size of stars from other studies through eclipsing binaries, through this particular method. And from that, we apply to exoplanets and we find what the size of the planet is. So eclipses are extremely important to measure fundamental properties of stars. If it wasn't for eclipsing binaries, we wouldn't even know how large and how massive stars are. Moving on, pulsating variables. which is actually an intrinsic type of periodic stars. These are variables that are single stars. And as single stars, they're going through a very special phase in their life, a step back. Stars are huge balls of gas. Those gas balls are controlled by two main forces. There's a force of gravity that keeps everything together. So this is a schematic more or less showcasing these two forces. Gravity pushes everything inside, tries to push all gas from a star, all atoms of that star as close together as possible. At the same time, at the very center of the gas, of the star, there is a nuclear factory in principle that is burning hydrogen into higher elements. As a result of those nuclear reactions, radiation is created that tries to pull all gas layers apart. So this is the force of gas pressure trying to actually pull everything apart. Now, for most of their lives, stars spend their time at a state where the force of gravity is balancing the force of gas pressure. And this allows the star to be in a steady state, an equilibrium state, if you will, which is actually called hydrostatic equilibrium. So at some point, though, so I'm going to play a little movie for you, showcasing more in fast forward, of course, how a star like that lives. Again, a big ball of gas where gravity and gas pressure are balanced, so just does its own thing. But at some point, hydrogen is being exhausted at the center of the star, and this equilibrium is being disrupted. And then a battle starts between gravity and gas pressure trying to dominate each other. Now, when gravity wins, the gas is compressed. When gas pressure wins, the gas layers are pulled apart. And this continues for a while until the star moves in the next phase of its life. So in principle, in this particular phase, the star contracts and expands, physically changing its size. These kind of changes are reflected in the light curve of a star. So you see increases and decreases of the brightness that are reflected by increase and decrease of the size of the star. And these are things that we can definitely observe. This is what we call a pulsation of a star. And actually, it showcases a very telltale of a star changing in size because of disruption in hydrostatic equilibrium. So why are these important? This is one of the pulsating star categories, what we call Cepheid variables. And they have a very characteristic shape, very characteristic timeline when it comes to the changes in its brightness. Now, here's a very interesting story. This young researcher who lived at Harvard, and was studying photographic plates. This was a way of taking pictures of the night sky in the previous century, beginning of the previous century. She was studying this little blob of gas in the night sky. This is an image of the southern hemisphere. Perhaps you have access to, could you see those actually? The Magellanic Clouds. This is the large Magellanic Cloud and the small Magellanic Cloud. These are satellite galaxies, nearby galaxies, completely outside our own, but galaxies that we can see from the southern hemisphere. Now, this woman was studying these types of stars, Cepheids, and she noticed that a large number of those Cepheid stars were concentrated in the vicinity of this galaxy, a lot of them. After measuring the periods of those Cepheids and the relative brightness of each one, she found a relationship between the period and apparent brightness for all of those stars, in that the stars with longer periods were brighter than stars with shorter periods. Using a simplified assumption that all of the Cepheids within the small Magellanic Cloud were at approximately the same distance, the apparent magnitude of each star is equivalent to its absolute magnitude offset by a fixed quantity depending on that distance. This reasoning allowed Leavitt to establish that the logarithm of the period is linearly related to the logarithm of the brightness of the star, the luminosity of the star. The luminosity of the star, in principle, is the amount of brightness radiated by the star in the visible spectrum. So from there, you can actually assume that there is a relation between the period and the absolute brightness as well. In astronomy, this is pretty much Leavitt's law. It's the period luminosity relationship, which is actually connecting the luminosity of a pulsating variable star with the pulsation period. The best known relationship is the direct proportionality law holding for classical Cepheid variables, called Leavitt's law, which is the luminosity L is 4 times pi d square, where d is distance, times b. So this is a law that connects the luminosity of a star with the distance. Why is this important? Because it is actually extremely valuable to measure distances in space. It's not easy to know how far stars are. There's no other yardstick that gives us a distance between us here on Earth and nearby star. There is no other way of actually telling how far galaxies are. And because, so if we find this kind of periodic variables at different parts of the sky at different distances, we can tell how far they are from here. And also we can tell how far nearby stars are. So this is what we call a distance ladder that allows us to actually measure distances out to specific parts of the universe. And the Cepheid variables are getting us all the way to nearby galaxies. So that's how we know how far the Magellanic Clouds are, how far the Andromeda Galaxy is, and they go all the way to M100. Studying Cepheid variables right now is extremely active research field. We still measure distances through them. Now, I'm going to switch gears again and talk about spotted variables. The prototype of those variables is our sun, our own star, which up to about 400 years ago was considered to be a perfect sphere. Perfect sphere means perfectly spherical and completely smooth. The first person who actually observed the sun and acquired observations of the sun was Galileo. And Galileo managed to actually document not only the fact that the sun is not a perfect sphere, in some cases actually has lots of abnormalities, but also at the outer layers have these dark dots that he calls sunspots. And those spots rotate with the sun. This is a part of Galileo's calendar, Galileo's log, actually, where he was recording different phases of the rotation of the sun, how it changed from day to day, and he managed to actually measure the first rotation period of the sun. Now, this is a cross section of the sun's anatomy, and it actually shows various layers, atmospheric layers. What powers the sun at its interior is a set of nuclear reactions converting hydrogen to helium at the sun's core. I talked about hydrostatic equilibrium, so the sun is in hydrostatic equilibrium right now. I can spend a whole lecture by itself talking about the sun, its structure and evolution, and all the phenomena that happen in our nearest star. And they're all related to solar activity. So I would like you to actually take a look, whatever resources you have access to, take a further look on our sun. It's a very, very interesting star. This is more or less what we can observe from the sun. This is part of solar activity. And you know, because the sun is the nearest star to us, we can actually study it in great, great details, and still we're finding new things. So what you see here is spots, sunspots, and actually those spots can be larger, way larger than the Earth, just for scale. What you see is what we call spicules here. These tiny microscopic movements in the in the layers of the sun and granulation. You see coronal mass ejections, you see prominences, you see filaments, you see all kinds of effects. And actually some of them does affect us here on Earth. And all of them have to do with the sun's magnetic field. Now, what is important for our purposes are two different facts. First, the sun does not rotate uniformly around its rotation axis. It's not a solid ball. That means that the equator here rotates faster than the poles. So it moves really much faster. The second thing is, so this is again possible because the sun is a gas. It's a big ball of gas. This is a phenomenon that is known as differential rotation, and it's known to exist in other stars as well. The second phenomenon is related to the sun's magnetic field. And the magnetic field is actually attached to different atmospheric layers. Just imagine a magnet, north and south, right? So the magnetic field will look like this, like a dipole. Because of differential rotation, the solar magnetic field, which is attached to the sun's atmospheric layers, is dragged along. And as it drags along, it's wrapped around the sun. And as a result of that, it creates little kinks that pretty much are equal to mini dipoles and pretty much emerge from the surface, from the outer atmosphere of the sun. In other words, it looks like that. So this is the magnetic field, and these are magnetic kinks that actually emerge from the specific layer of the sun. At this point, where the magnetic field emerges from the outer layer of the sun, the magnetic pressure that is actually demonstrated by B squared, where B the magnetic field, over 8 pi, is larger than the gas pressure, NKT. This is from your thermodynamics. I'm sure that you know this. And as a result, this particular part is being suppressed by the magnetic pressure, and it appears to be darker than the rest of the photosphere. And this is the underlying cause of spots, of sunspots. Now, why is this important? Because sunspots are attached to the photosphere of the sun, as the sun rotates around its axis, spots come in and out of our line of sight, and they change the light we get from the sun. We now know that such spots exist in all stars with a magnetic field, every star with a magnetic field, which is pretty much most of the stars that burn hydrogen in their core. If we monitor any of those stars, we see those spotted regions coming in and out of our line of sight, and that has an effect in the brightness of the star as well. So by measuring how long those spots take to make a revolution around the star, we can measure the rotation period. Not only that, we have discovered that there is a relationship between the rotation period of a star, how fast it rotates, the number and intensity of star spots, and its age, in that the faster the star rotates, the more active it is, meaning that it has more spots, and actually larger spots, and larger signals in the light curve, and it is younger. So younger stars are much more active than older stars. This is what we call an age-activity rotation relationship, which actually allows us to calculate the age of stars in the universe. It's really very difficult to actually tell how old a star is. They don't come with birth certificates to know when they're born. So using this age-activity rotation relationship, we are extracting fundamental properties of stars, such as their age. I'm going to switch gears again and go to some of my favorite objects, which are called explosive variable stars. And actually, we're going to focus on one subcategory, what we call cataclysmic variables. These are semi-detached binary star system, in which one of the stellar components is a white dwarf, a white dwarf, and the other one is a normal star. Step back. A white dwarf is a star that has the mass of the sun, more or less, squeezed to the size of the Earth. So it's an extremely dense star. And as a result, it has a very strong gravitational field, extremely strong gravitational field. So this is the Roche-Loeb geometry of the two stars, and pretty much an artist's conception, an artist's rendering, how showcasing the main parameters of a system like that. The donor star, the sun-like star, is actually filling its Roche-Loeb, and as a result, material escapes from the Lagrangian point and is accreted onto the white dwarf through what we call an accretion disk. So here's a schematic that shows the same system. You see the sun-like star, we're going to call it a secondary or a donor star, mass donor star, the star that gives mass to the white dwarf. The white dwarf is here at the very center of the star, of its Roche-Loeb, and at the very center of what we call an accretion disk. This is how mass is transferred from one star to another through what we call a stream, an accretion stream, and this is an accretion disk. And actually, both stars are moving around the common center of mass. This is still a binary star system. Now, for simplicity, we will focus on systems where the white dwarf magnetic field, which is actually depicted here, doesn't have any real effects on the accretion process. What controls all the phenomena in this system is pretty much the mass accretion rate, how fast material is transferred through the in-Lagrangian point. And that actually controls how bright the star is and how it evolves. So this is the luminosity of the system and its relationship with the mass transfer rate, which is actually the mass accretion rate, the rate at which mass is transferred from one star to another. A very simple equation, but this pretty much shows that if the mass accretion rate is large, then the luminosity of the system is large. So if the mass accretion rate increases for whatever reason, then the luminosity of the system increases. How does this look like? Well, here is a case where the mass transfer rate is low. And by low, I mean 10 to the minus 5 to 10 to the minus 7 solar masses per year. Again, this is a depiction of the system. It's a star, a normal star, a sun-like star. There's a white dwarf, accretion disk, hotspot, the accretion, which is the point that the accretion stream hits the accretion disk. And this is how, this is actually a long-term light curve from the AAVSO data. Pretty much what you see here is this is the baseline level of the star's brightness. But from time to time, this baseline level is increasing with time in what we call an outburst. A dwarf, and this is actually what we call a dwarf nova. A dwarf nova outburst is a result from temporary increases in the rate of accretion on the white dwarf caused by additional material accreted on the surface. The material must go through a violent transition region called the boundary layer, which lies just above the surface of the white dwarf. Now, white dwarf outbursts are because of materials just pushed inward to the white dwarf for whatever reason. We don't really understand how this happens, but we see it in the light curves of the system. It's not exactly periodic. We cannot really predict it, but by observing it, we try to understand the way that materials transfer from one star to another. This is very active research right now. Again, we don't even know for sure what controls the mass accretion rate, why some stars have lower than and some other stars have higher mass accretion rate. But this is actually why it's really important to keep observing those stars. How about the high mass accretion rate? These are stars that have accretion rates 10 to the minus 7 to 10 to the minus 8 solar masses per year. These are, and they're known as novae. In this particular case, the white dwarf collects material in a really high mass transfer rate. Material is accumulated on a layer surrounding the white dwarf. And because of the high mass transfer rate, it does not have time to mix with the interior layers of the star. As a result, the material forms a layer of nuclear fuel on the white dwarf, like a blanket. Now, the bottom of this layer is gradually compressed by the surface gravity of the white dwarf, and ultimately it becomes electron degenerate. As a result, pressure and temperature increases and reaches a point where the star goes through a chain of nuclear reactions called thermonuclear runaway. This leads to a spectacular explosion. This leads to an explosion where the star ejects its outer layers in the universe. The way that we actually see this eruption, this nova eruption, is by an increase of the brightness of the system by more than 10,000 times, actually a million times. And actually, as it's very intense, it's very quick, and then afterwards we see a very gradual decrease of the brightness of the system as material is actually expanding from the white dwarf and it clears up. What you see here is also a very dramatic dip in the light curve. This is time, and this particular time is in months. So the time scales are really large. And these are AAVSO light curves, actually, in different filters. This dramatic dip is because as hot material is expanding, like in here, at some point it condenses and it forms dust. And dust in the universe acts like a blanket. It covers light. So you see a dip in the light curve because of this dust. Some systems form dust, some others don't. And we really don't understand why this is happening. That's another research topic for you. This here is a Hubble Space Telescope. This is an artist's conception of how a nova eruption looks like. This is a Hubble Space Telescope picture of a nova. The binary is at the center of this picture, and we're not able to see it. All we see is the hot gas that's ejected from the binary, which resembles a ring in this particular case. Now, remember, a nova eruption does not destroy the star, the white dwarf or the binary system. Accretion continues at the same levels. So as the white dwarf collects more material, the same conditions that lead to thermonuclear runaway occur more than once. In this case, we see more than one nova eruptions from the same system. We don't really know, again, why we see more than one nova eruptions, or we've seen more than one nova eruptions in some systems, but not in all of them. What we suspect is the time that it takes for the white dwarf to reach conditions for a thermonuclear runaway changes from system to system. So every nova will actually show another eruption. But again, we don't understand why we haven't seen them all. This is, though, an example of a nova, a system that did show multiple eruptions. This is another field star. It has nothing to do with a nova. The cataclysmic variable, the progenitor of the nova, is at the very center of this big ball of gas. And what you see here are remnants of the multiple eruptions. Within 100 years, this particular star has shown about 4 or 5 eruptions. The first one was observed in 1890, then 1902, 1920, 1944, 1966, and another one in 2011. So every 22 years or so, more or less, this system is showing one nova eruption, which is very interesting to see. And actually, a big puzzle was why it did not show an eruption between 66 and 2011. And we're still trying to even understand it now. High mass, there are times where the white dwarf does not eject all its layers and it keeps growing in mass. In this particular case, the mass of the white dwarf increases at its interior until it reaches 1.4 solar masses. Why is that important? Because 1.4 solar masses, what we call the Chandrasekhar mass limit, is necessary to trigger the burn of carbon inside the white dwarf. This triggers a massive explosion that completely destroys the star. ejecting large amounts of radioactive nickel and cobalt and argon and calcium, all kinds of types of chemical elements in the interstellar medium. And this is what we call supernova 1A. So supernova 1A are white dwarfs that reach this Chandrasekhar mass limit and explode. This completely destroys the star. This is the end of the binary. This is the end of the white dwarf. And as a result, a wealth of chemical elements in the periodic table are formed. So if you pay attention to the here, everything that is coded by light blue, all those elements are being formed in exploding stars of this particular type. So we're talking about, again, silicon, argon, calcium, titanium, vanadium, chromium, nickel, cobalt, you get the point. Most importantly, these are extremely bright, extremely bright. We can see them at galaxies very, very far away, almost at the edge of the universe. This is an example of a spiral galaxy. It probably has a black hole at the very center. And this bright dot here at the outskirts of the galaxy is a supernova of the type that I showed you. Not only that, they appear in all types of environments. They are independent of the type of galaxy. We can see them in both spiral galaxies and in elliptical galaxies. So this is a spiral galaxy. This is M101, a very, very popular galaxy to study. The center of the galaxy here, the spiral arms, which are actually brightened by star formation regions. And you see a very bright spot here, which is actually a supernova of the type that I described to you. This is another example. This is a supernova here. And this is an elliptical galaxy. Elliptical galaxies are very inactive, very quiet. They don't show any structure. They're very smooth in their phenomenology. Here's the center of the elliptical galaxy, and here is the supernova type 1A that I described to you. And actually, one thing that you can see is in this particular case, the supernova can be as bright as the galaxy center as well. Now, exactly because all phenomena, all supernova 1As are the result of a white dwarf that reaches that particular mass limit, their light curves and their spectra look exactly the same, no matter what you look at or which phenomena, which event you look at. This is a light curve that is of different events. Again, brightness change with time. 0 days is the maximum of the brightness. So as the star explodes, the light, the brightness of the star increases and then decreases as the event ends. Different colors represent different events. So if you follow the blue dot, these are data that are taken of one specific supernova. And you can tell that no matter which dot you follow, everything falls on this particular curve. So they look the same. Light curves are the same. This is actually, again, a very characteristic spectrum that is pretty much showcasing all kinds of elements that come out from this particular supernova, this particular type of supernova. Now, that makes supernova 1As as standard candles. Now, standard candle is an astronomical object that has a known absolute magnitude, a known magnitude at its peak, at the very peak of the light curve. They're extremely important because if you also measure the apparent magnitude of the object, the brightness of the object as it looks here from Earth, we can determine the distance to the object. So in this particular case, the distance to the supernova, for supernova 1As, right, is the absolute magnitude, which is the same for all events at maximum, the apparent magnitude, m, which is actually, the brightness of this event as we see it from the Earth, in this very, very simple formula. That's it. That's all there is to it. And exactly because those events are extremely bright, Supernova 1As are taking us very deep in the universe. So we actually can study galaxies at the very beginning of the universe through them. So, and we're still using this method in order to go to galaxies very far away. Not only that, if we know the distance to the host galaxy and we measure how fast the galaxy is moving away from us, what we call a redshift, we can do cosmology and figure out fundamental properties of the universe. The data that are summarized in this illustration involve the measuring of the redshift of the distant supernovae, which is actually the same thing as how fast they move away from us. And different scenarios for the universe that are tested during this method. So using supernova 1As, knowing the distance to the supernova and measuring how fast they move away from us, we know now, we found out for the first time the universe's history. We know that the universe is expanding. Not only it's expanding, it's accelerating, and there's something that we don't understand quite well yet that is called dark energy that is driving this acceleration. And if you're wondering if this is an important find, in 2011, the Nobel Prize in Physics was assigned to two different teams of astronomers for the discovery of the accelerating expansion of the universe through observations of distant supernovae. So this is an extremely important result. And again, a very active form of research right now. I hope I gave you an idea of why variable stars are very important for the study of the universe, what kind of information we get about fundamental stellar properties, and why we study them, why we invest all these research hours, and how they can actually, we're using physics in order to extract properties of stars from light curves. We get information about fundamental properties such as mass, radius, age, luminosity, temperature, the star's internal structure, whether it changes this hydrostatic equilibrium, magnetic fields, stellar evolution, how stars evolve. We're defining the distance ladder through them. We measure distances, and that is extremely important in the universe. I cannot say this enough times. We actually find out about the beginning and the future of our universe, cosmology. We have formation of elements heavier than helium and hydrogen, and also planet formation conditions for life through variable stars. The AAVSO actually has a super catalog that classifies all those variable stars and makes them available to the community, the Variable Star Index, VSX. From there, you can actually search any information that you want and find more about individual variable stars, pretty much everything that is known for them, such as periods, eruption history, discovery history, where they are in the night sky, how bright they are, and what is the brightness variation, et cetera, et cetera. I would like to leave you with a final thought. We live in the renaissance of variable star astronomy. There are multiple space and Earth missions that aim at exploring the night sky, and what they produce is a plethora of mysteries. They produce new exoplanets, they produce new pulsating variables, new eruptive variables. There's not enough professional telescopes to actually follow up those targets. And this is what we do here at the AAVSO. We engage citizen scientists, individuals who have their own telescopes, to actually go and observe light curves and collect as much data as they can of objects of interest to actually make them available for the scientific community. So with that, I would like to actually encourage you to become a member of the AAVSO. The membership is $25 if you are in Bangladesh or India. So it's really very affordable. But at the same time, check out all the resources we have about variable stars, how to observe them, and also consider taking one of our online courses. Perhaps they can actually help you start your own observing program. With that, I would like to thank you and ask if there are any questions for me.
Thank you, madam, for your wonderful presentation. I think students have learned a lot of things about the universe through variable star. So if you allow us, so we can start our discussion session. We have got some question in inbox and in comment. So if you allow, we can start our discussion session.
Yes, of course. I'm stopping my screen.
So what are
All
the,
right. How are we
okay,
going? Yes.
I can add the question in the, if you, so, but dear ma'am, I have a question. Black hole attraction all things. So graviton particle are situated in their gravitational field. Black holes attraction all light particle, photon particle and graviton particle are living in the gravitational field. How two particle live there another by another or with together?
What happens in black holes when you get to that point of cellular evolution is a very active form of research. The answer is we do not know. We just don't know. We don't know what happens inside a black hole. And we still try to understand how material forms even inside neutron stars, what exactly the form of matter is in there. There are lots of theories, lots of theoretical concepts, but again, I'm an observer, so I would rather tell you things that we know from observations. At this point, we don't know, really don't. It's an excellent question.
Thank you, madam. So we have another question. So, does quantum loop theory disagree with string theory, and why?
Ooh, that is completely outside. I'm
Yeah,
going to skip
different.
this question because
Okay, so
this is not my area of expertise.
okay, so tell me another question. Is there any effect of dark energy to this variable star?
The one effect we know of, that's a great question. The one effect we know of affects how fast stars move away from each other, how fast the universe is accelerating, not of specific stars. Does this make sense? We know though that there's lots of dark matter between stars. Dark matter is material that is not emitting light, so we cannot detect it. All we can detect is the gravitational interaction with these objects around it, and we know there's lots of dark matter even in star clusters. So, yeah.
Thank you, madam. There is the final question in the inbox. So, what are the eclipsing of the binary star? Maybe you have explained in your presentation.
Say it again, please.
What are the eclipsing of binary star?
What are eclipsing binary stars? There are two stars that are passing in front or behind each other, and they cause a dip in the brightness of the system. Remember again, even when you have binaries, two stars together, we don't see the two stars. The only reason we know there are two stars is because of eclipses. The one star passing in front or behind the other and causing this dip in the light curve. Light curves is the key to the universe, pretty much, or one of the keys. Spectra is another. So the only thing we see as astronomers, and this is what I find fascinating about astrophysics, all we have is light in our hands. We can't go close to a star. We cannot take a scoop of a star and take it to the lab. We just can't. All we see is light. The only one star that is close to us is our own star, the sun. And all we do again is take pictures of it, right? So we can't go there and grab material. So we're trying to be smart and inventive and innovative when it comes to studying this light. We're trying to invent more techniques and look at this the starlight in different ways. And that's all we do as astronomers, actually. And of course, we use physics in order to understand how things interact. Physics pretty much is the language for astronomy, is the language for everything describing the world around us. So I actually commend you for studying physics. I'm a physicist as well. So I love it.
Yeah, thank you, madam. So we have another question. So, dear madam, are there more than one type of dark energy particle with a defined constant energy density exists? It may solve cosmological coincidence problem.
The answer is not that we know of. We don't know of different types of dark energy. Remember, dark energy is not particles, it's energy. It's radiation of some sort, right?
you. So it is a very great webinar with you, madam. So I think students have learned a lot of things about this variable start. So you have already mentioned about the online course. So if any of our students want to do their astronomy course in online in your institute, what she or he need to do for that? Is there any funding for that?
Why don't you send me an email? AAVSO@aavso.org. We'll think about that.
Okay,
Actually,
thank you.
the first course has to do with statistics. So it's a statistical way of studying the universe. And the second one talks more about light curves. So what kind of information we extract, why we should care. I mean, it gets more in depth than what I covered within the last hour.
Okay. So thank you,
But
madam. So
actually, I would open it to your students.
yeah, thanks. Thanks a lot. So we'd like to say thanks again on the behalf of the Department of Physics, Pabna, University of Science and Technology, madam, for accepting our invitation and for giving us time in this corona pandemic situation. As we know that you are too busy with your works. So hopefully in near future, after the COVID, we will definitely invite you for a face-to-face session for a
I would love
student.
that. That would
Yeah,
be wonderful.
thanks.
Yeah. That would be wonderful.
Thanks, madam.
So, for all of you, stay safe.
Yeah,
And
that's
we
the
will get
important
through.
thing.
Yes.
Yeah,
Yeah.
we have to be careful about this situation. So thanks again, madam. Bye for today. Good night.
Have a good night. Bye.
Yeah. Bye.